Today we're going to continue talking about network flow. In the last session, we saw the basics of what a flow is, and we also saw the very important Ford-Fulkerson algorithm. So the idea in the Ford-Fulkerson algorithm was that I keep track of the residual graph. And remember that the residual capacity on every edge was the original capacity minus the amount of flow that I was sending over that edge. And then every time I just did a DFS from my source vertex and I tried to find a path to my target vertex, but I did this in the residual graph, not in the original graph. And whenever I found a path in the residual graph from the source vertex to the target vertex, I would just use that path to augment my flow, to increase the amount of flow from S to T. And this was the Ford-Fulkerson algorithm. So very simple. I start with a flow that is just 0. And then I say that as long as I can find a path in the residual graph, use this path to increase the amount of flow. Okay. Now, the Ford-Fulkerson algorithm doesn't really say how to find the path. So we're just going to do the most natural thing and use a DFS. And we saw that the runtime here would be O F times M, where F is the amount of flow, and M is the number of edges that we have, and we were assuming that we have more edges than vertices. Okay. We proved its correctness and everything in the last session, but we also ended up finding examples where the Ford-Fulkerson algorithm is really terrible. For example, we saw that here it can take 10 to the power of 20 iterations or augmentations, actually 2 times 10 to the power of 20 augmentations to find the path, to find the maximum flow from S to T. Now, of course, the main problem is that this runtime of O F times M is not really polynomial. Of course, it's polynomial in F and M, but F itself can be exponentially large. As you can see here, I can basically have any number as the capacity of my edges. So I don't really like this runtime. And so the whole point of this lecture is to first show you how to code Ford-Fulkerson and then show you how to improve the runtime, how to do things that would actually reduce this runtime to a polynomial runtime. And when I say polynomial, I mean based on the number of vertices and edges, right? So it shouldn't depend on something like this. So let me start by just showing you how to code Ford-Fulkerson. Okay, I'm going to start by just reading the input here. And yeah. Let's say that I read the number of vertices, the number of edges, and also my start and end vertex, so S and T. And actually, let me put this out here, N, M, S, T. So I'm going to read N, M, S, and T. Now, what are the things that I want to keep track of? I want to keep track of my original graph, which is basically a bunch of capacities. Right, we said that an edge exists if and only if the capacity is not 0. So I can just save all of the capacities. I want to also keep track of the flows. And of course, I also want to keep track of the residual flows. So, residual capacities. So this thing. So I want these 3 basically. I want to know the capacity C from every vertex U to every other vertex V. I want to know the amount of flow that I'm sending from U to V. And then I have the remaining capacity or residual capacity, which is just the result of subtracting this. Now, technically, you can just save these 2 and not bother with R at all. But I'm going to save all 3. Okay. So let's say I have some maximum N. And I'm just going to use something small for now. And then I'm going to say I keep my capacities and I keep my flows. This is also max N by max N. And I'm going to keep the residual capacity as well, max N by max N. Okay. Other than this, I want to also save my original graph. But I don't really care about the direction of the edges in the original graph, because here's the thing. If I have an edge from U to V in my original graph, what does that tell me? It tells me that in my residual graph, I can have an edge from U to V or from V to U, right? So I kind of lose the direction, but I want to have a concept of what are the possible edges that I have to look into when I want to do a DFS, for example. Okay, so I'm just going to keep track of the neighbors of every vertex in my original graph, and I'm going to ignore the direction of the edges when I'm defining neighbors. So I'm just going to keep a vector of neighbors for every vertex. Okay, so reading the input, let me read all of my edges. So I say that for every edge, I read U, V, and let's say W. And the idea is that this is an edge from U to V with capacity W, okay? So I'm going to say in the set of neighbors of U, I want to push back V. In the neighbors of V, I want to push back U. And then I also want to say that the capacity from U to V is now W. Okay. Now, because I'm also saving the residual capacities and because I'm starting with the flows being 0, I have to say that the residual capacity from U to V is also W, right? So here I would say the residual capacity from U to V is the same as the original capacity from U to V. Okay. Now, the actual algorithm, I want to say as long as there is a path from S to T in the residual graph, augment the flow using this path. So suppose that I have a DFS function, and let's say that my DFS function returns true if it gets to my sink, to my target T. Okay, so I'm just going to have a DFS function that returns a Boolean. I will come back and write that later. And here I just want to say, while you can do a DFS starting from vertex S and it returns true, as long as you find the path to the vertex T, just do the augmentation. Okay, increase your flow. Now, I'm gonna write my DFS. Of course, in order to write DFS, I have to keep track of which vertices are seen and which vertices are not seen. But some point that is sometimes leading to bugs is that every time I do a DFS, I have to reset all of this. I have to clear basically everything that I have seen. So let's say I also create a function called cleanup, which just does the cleanup after the DFS so that the next time I want to do DFS, everything is clean. So let's say I have my cleanup here. And in this cleanup, I'm just going to say for every vertex, for every I from 1 to n, scene of I is false. So I haven't seen it. And let's say that in my DFS, I'm also going to keep track of the path that I have seen so far in my DFS. So let's say this is the path that I'm taking starting from S, and I will stop adding to this path as soon as I reach T. So in my cleanup, I'm going to say, let's just clear the path as well so that the next time I'm finding a new path. Okay, now my DFS. I'm doing the DFS starting from a vertex U. The first thing I say is that if U is the same as T, then just return true. Because that's the whole point. I want to see if I can reach the vertex T. And if I reach T, I will not continue my DFS anymore. And of course, I have to also say that scene of U is true. And then I say, let's go over all of the neighbors of U, and let's see if I can go to them. So I say for every vertex V that was in the set of neighbors of U. Now, when can my DFS go from the vertex U to the vertex V? Well, I have to say that I have not seen V before, but also remember that I'm doing this DFS in the residual graph. So I can go from U to V only if R of UV is greater than 0. So I say if I have not seen V and R of U and V is greater than 0, now I can do a DFS from V. Okay. And if all of these DFSs end, and if none of them return true, I have to return false in the end. So actually here I have to do it like this. I have to say if DFS V, so if I went to V and from V I could reach my target, then return true. But if I didn't return true and I finished seeing all of my neighbors, then I'm gonna return false. Okay, so right now my DFS just tells me whether I can reach my target vertex T. But I wanted something more. I wanted to also keep track of the path that I'm taking all the way to T. So let's say every time that I seen a vertex U, I add it to the end of the path. Okay. And every time that I'm returning false, I'm realizing that, well, from this vertex, I couldn't get to the target. I'm going to remove it from the end of my path, right? But in the cases where I'm returning true, I'm gonna just let it remain on the path. Okay, so in the end, if my DFS returns true, this path will have exactly the path from S to T that my DFS has found. Okay, now finally, I have to write the augment function. So the augment function just assumes that this path is given and has to do augmentation over this path. Okay, so let's do augment. Now, first of all, I have to figure out what is the minimum capacity over all of the edges in this path, right? Because when we were doing flow augmentation, remember in this residual graph, I was finding a path, and then I had to decide how much flow I can send through this path. And the amount of flow that I could send was basically the minimum remaining capacity among all the edges in this path. So let's find that. I can do something like this. I can say, look at all of the vertices in this path. Let's say that vertex U is the ith vertex, and let's say that vertex V is the I plus first vertex. That's why I had less than path.size -1 there. And I just want to look at the residual value from U to V. So let's say I have some value, and my value is initially a huge number. Remember, because of 2's complement, I can write something like this, and this is actually the biggest number that fits in int. And then every time I say my value becomes the minimum of my value and the residual capacity of the edge UV. Okay, now I found how much flow I can send through this path. I have to now go ahead and actually do it. So I have to go over this path again. And I have to send the flow. So again, let's say that U is the ith vertex of the path and V is the I plus first vertex of the path. Now, I want to increase the flow from U to V by this value that I calculated here. Okay. What are the things that would change? Well, F of UV has to increase by this value. Okay. But remember, F had this property that F of VU was minus F of UV, right? So F of VU has to decrease by this value. Okay. So that's what I have to do with F. Do I have to change anything in C? No, because C was my original capacity. But I have to also update my value of R. So R of UV actually decreases by the value and R of VU increases by the value. Right. Or if you don't want to remember all of these things, you can just write R of UV equals C of UV minus F of UV. This is also fine. Right. I'm just using the definition of R. And the same thing for VU. So R of VU is C of VU minus F of VU. Okay, this is the augmentation. That's everything I had to do. And now finally at the end, I can print my flows. So let's say for every I from 1 to n, and for every j from 1 to n, I just print the flow from vertex I to vertex j. Okay. And if I want the amount of flow, I can just look at the sum of the flows that are going out of my vertex S, right? So I can say my flow amount is 0, but for every I from 1 to n, I increase my flow amount by flow of Si. And then I say that the max flow is this. Okay. Let's give it an example. Let's give it an example like this, actually. So let's say I have to give the vertices numbers. So let's say this is vertex 1, which is also my source. Let's say this is vertex 4, which is also my target or sink. This is vertex 2. This is vertex 3. Let's say I have 3 here, 2 here, 2 here, 3 here, and 1 here. Okay. What is the flow that I can send? What's the max flow in this case? It's actually 5, right? Because I can send like 2 units like this, I can send another 2 units like this, and I can send 1 unit like that. So let's see if our algorithm works. So I have 4 vertices. I have 1, 2, 3, 4, 5 edges. I want to go from vertex 1 to vertex 4. And my edges are 1, 2 with capacity 3, 1, 3 with capacity 2, 2, 3 with capacity 1, 2, 4 with capacity 2, and 3, 4 with capacity 3. And as you see, it found the flow matrix, and it says that the max flow is 3. Okay, great. So this is the Ford-Fulkerson algorithm. But of course, we've seen that in the worst case, it can find this augmenting path and then this one over and over again, and it can take a long time. Honestly, it's really hard to implement it so that it always goes through the worst case, because the DFS just finds some path. You don't really have any control over how your DFS finds a path, right? So if I want to actually make this worst case happen, I have to think a lot about how to label the nodes and so on, but we know that this is the worst case. So let's now talk about how we can improve the runtime. So the first idea, which I also kind of mentioned last time, is the idea of Edmonds-Karp. And this is a very simple idea. In your residual graph, you want to find paths from S to T. Now, Ford and Fulkerson just say, find the path using any algorithm, and we were using DFS. Edmonds-Karp say, instead of using a DFS, use a BFS to find your path. So find the path that is as short as possible. But here, when I say short, I mean the number of edges. Okay, I want to have a path with the smallest number of edges. Okay, so this is basically Edmonds-Karp is just Ford-Fulkerson with BFS. Okay, so basically, I want to take my code here. I have a DFS. I want to replace this with a BFS, and everything else remains the same. So let's do this, and then we will come back and talk about the runtime. So let me copy Ford-Fulkerson, and let's call it Edmonds-Karp. Okay. I'm just gonna say while BFS from S, and I'm gonna write a BFS. It has a starting vertex U. And well, this is again just like a BFS. I should just have a Q because I'm doing a BFS. So let's say I have a vector called Q. This is my BFS Q. And then initially, I would just push in this vertex U. Actually, I don't even need to pass the U because I'm not writing it recursively. So I know that my BFS is always from S, right? So I say sin of S is true, and Q dot pushback S. And let's say, actually, because I want to take from the beginning of it, let's say this is a deck. I could also use a Q. Yeah, this is fine. But let's say I want to also save my BFS tree. So let's say that for every vertex, I want to save who the parent of this vertex is in my BFS tree, because that would help me find paths in the BFS tree, right? So I'm just gonna say here maybe instead of all of these things that I have, let's also have a parent for every vertex. And let's remember that when I'm doing my cleanup, I set the parents to 0 as well. Okay, I have a bunch of things that I don't need anymore, but I don't want to clean up my code right now. So let's say I'm just going to use this. And initially, the parent of S is S itself, right? Now, I'm just going to say, as long as this Q is not empty, take some vertex U from the beginning of the Q, and then, of course, pop front, remove it. Now, I want to do my BFS from the vertex U. But where can I go from U? I can go to any neighbor that is not seen, but I'm also doing the BFS in my residual graph. So I can go to a neighbor V only if R of UV is greater than 0. So I just say for every vertex V in the set of neighbors of U, if I have not seen V before and R of UV is greater than 0, now I can put V into my Q as well. So Q dot pushback V. Let's say that I set sin of V to true already here. And I say that the parent of V is U. Okay. And of course, I continue this until I see my target vertex T. Or I can just say, whatever, continue your BFS, go see whatever you can see. And in the end, just return sin of T. So if you've seen the vertex T in your BFS, you return true. Okay. Now, the other point here is that I have to also create this path so that I can augment it later on, right? So I want to say if I have seen T, if seen T, create the path that starts from S and goes to T. But how can I create that? I can just start at T and just keep going to the parent of T in my BFS tree until I get to S, which is the root of the BFS tree, because I started my BFS from S. Okay, so I say, let's start from the vertex T, and as long as parent of U is not U, let's say, in the path, insert U and make U to be its parent. So I'm starting at T, and I'm just going up my BFS tree until I reach to the root. And I'm creating this path. Actually, this is not good because it's not pushing S itself. So let's do something like this. And let's just say if U is equal to parent of U, then break. This is better. Because now it starts at T, it adds the parent of T and keeps going until it reaches S, adds S, then it sees that it's the same as its parent and it stops. Okay. Now I have to make this one. This one was vector. I have to make it into a deck as well. But everything else is the same because now I have found the path. And after finding the path, all I'm saying is do the augmentation. It's just that I found the path using a BFS instead of a DFS. So if I don't have any bugs, this should work. Oh, I forgot to copy the input that I gave to the last one, so I have to do this again. 4 vertices, 5 edges from vertex 1 to vertex 4. 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 4, 2, and 3, 4, 3. Okay, and this is now not working for some reason. Okay, what's our bug? Let's see. I'm saying while I'm doing the BFS, do augment and then do cleanup. I know that my augment is correct. My cleanup sets the parents to 0, sets the scenes to false, clears the paths. Okay, my BFS starts with a BFS Q. Q dot pushback S, parent of S is, let's say, 0. While Q is not empty, take the first vertex off of your Q and look at all of its neighbors. If there is a neighbor V that is not seen and I have some residual capacity to it, pushback V, say that you have seen V, seen of V is true, and parent of V becomes U, okay? If I've seen T, make U equal to T, so start at vertex T. I'm probably having a problem here. So let's see. U is T while 1 pass dot push front U, and then U becomes the parent of U. And okay, I can now just say it like this. I can say while U is not 0. This should fix it, hopefully. Okay, so my part was that part. Okay, so it's giving the same result and the max flow is 5. Great, but why does this change our runtime? Why would this make our algorithm faster? Now, this is the part where we have to come back and really analyze what's happening in Edmonds-Karp. So let's say that I have my residual graph GF, right? And let's say I have my starting vertex S, I have my sink vertex T, and let's say I have a bunch of vertices in between. Okay, and I have some edges. Right now, I don't care about the weights of these edges. I'm just looking at the edges in my residual graph, okay? So let's say this is vertex 1, 2, 3, 4, 5, 6. And let me have something like this as well. Okay. Now, basically what Edmonds-Karp is saying is that in this residual graph, I'm going to use a BFS to find the path from S to T. So I'm always going to find the shortest possible path from S to T. But if you remember the lecture on BFS, whenever I do a BFS from some particular vertex, for example, from the vertex S, I'm basically dividing all of my vertices into several different groups or levels based on their distance to S. Okay, so I can do that. I can see what is the distance of every vertex. So the distance of S from itself is 0. Both of these vertices are at distance 1, right? And then these vertices are at distance 2. And then these vertices are at distance 3, and T is at a distance of 4. Oh, sorry, no. T is at a distance of 3. There's an edge from this to it. Okay, I just realized I don't like to have that edge, so sorry. Let me erase this edge. Let me change my graph. Let's do this, and now I'm right. Okay. So I can just write the distances. Now, here's what I can do. I can say that, well, if I want to find the shortest path from S to T, I really only care about the edges that go from one group, from one distance to the next distance, right? So if I'm finding any path that goes from S to T, this path is going to start at a vertex that has distance 0, and then go to a vertex that has distance 1, then go to a vertex that has distance 2, and so on, right? Otherwise, this would not be a shortest path. So I'm going to create a subgraph of this graph, and I'm just going to call it GF bar, let's say. And I call this the nice subgraph of my residual graph. So this is my nice graph. And what my nice graph does is that it only has the edges that go from one distance to the next distance. Okay, so it has all the same vertices. So let me just copy my residual graph. It's basically the same graph as my residual graph, but I remove all of the nonsensical edges that I know I will not take. Okay, so this is a good edge because it's going from distance 0 to distance 1. This is also a good edge, but this is nonsense. I don't need this one because it's going from distance 1 to distance 1. I would never take it in a BFS, in a shortest path, right? This is going from distance 1 to 2. This is good. This one's going from 1 to 2. That's good as well. This is going from 2 to 2. I'm going to remove it. This goes from distance 2 to 3, from distance 2 to 3. These are all good. This is going from 3 to 3. I'm going to remove it. And just to give you an example, suppose that I had this edge. Then this edge is actually going from distance 3 back to distance 1. I would never take this edge in a shortest path either. So I wouldn't put it in my nice graph. Okay. So my nice graph is just a subgraph of my residual graph. The only difference is that every path in my nice graph is the shortest path from S, right? So the only way that I can reach any vertex here, any path that I take here, would be a shortest path in this original graph, right? Okay, great. So now I'm going to use this nice graph to analyze the runtime of my algorithm. Remember, in my implementation, I wasn't even creating this graph. So this is just a mathematical object that I'm going to use for my runtime analysis. Okay. So here's the thing. What happens the first time I want to augment my flow? Basically, I'm going to find a path from S to T in my residual graph. And that path is the shortest path. So that path also exists in my nice graph. Okay, so I'm going to find some path here, basically. Let's say this path. And I'm going to augment it. Okay, now when I augment this path, so let's say I have this path here. And of course, because the nice graph was a subgraph of the residual graph, I have it here as well. Okay, so let's say I augment the blue path. What happens to my residual graph? What edges can possibly be added or removed in the residual graph? Well, first let's talk about the edges that can be added. I'm sending a flow from S to T through this path. So I will have all sorts of reverse edges getting added, right? So I will have edges like this. These edges will be added in my residual graph because the flow that I send can be unsent, basically, right? Okay. So can I possibly add any other edges? No, these are all the edges that can be added by doing an augmentation of this path. But now here's my question. Do these new edges, the magenta edges, actually change my nice graph? Now, not really, right? Because just look at these magenta edges. They're going in the opposite direction of this blue path, which was the shortest path. So every edge in the blue path was going from some distance to that distance plus 1. Every edge in the blue path was increasing the distance. So every edge in the magenta path is actually decreasing the distance. So none of them will appear in my nice graph. Okay. There is, of course, one special case, and the special case is if the distance from S to T increases, right? But as long as the distance from S to T remains the same, so the distance from S to T, originally it was 4. Let's say that after I did the augmentation, the distance from S to T is still 4. If that's the case, then T is in this group, in the group of vertices that have a distance of 4, right? So this previous vertex is in the group of vertices that had a distance of 3. But I know that there is a path from S to T of length 4. It doesn't make sense for me to ever take this edge. I would never take this one because it's going from distance 4 to distance 3. By the same argument, I would never take this edge and so on. So even though my graph might change, none of these edges will be added to my nice graph. That's the point that I want you to really understand here. Okay. So the only case that I might get some new edges into my nice graph is if, because of the augmentation, the distance from S to T somehow changes, increases. Right? So, because this whole argument was based on the assumption that the distance from S to T did not change, it was 4. Because remember, I was saying I have these different groups of vertices here. I have the level 0, which are vertices that are at a distance of 0 to S. I have level 1, which are distances at a level of at a distance of 1, distance 2, distance 3, distance 4, so on. Right? So the whole point that I was making, saying that I will never use those edges, is that the distance from S to T was 4, and even after the augmentation, I'm assuming that it remained 4. If that's the case, it would never make sense for me to take any of these magenta edges in my next augmentation. Okay? But of course, if the distance changes, if I do an augmentation and somehow my residual graph changes so much that the distance from S to T is now 6 instead of 4. Then, of course, I have to go and create a new nice graph because all the levels have changed and everything is different. Okay? Great. So what does this tell you? This basically tells you that I have a limited number of times that I'm augmenting with paths of any given length. So for example, the way this is going to work is that I do a BFS, let's say I find the path of length 1 and I augment it. Then I do a BFS the next time and the path would be longer. I would find the path of, let's say, length 2 and I augment it and so on. Maybe I have the same length several times, but my length never goes down. It can only ever go up, right? So the distance from S to T cannot decrease by this magenta edges, again, because they're all going in the wrong direction. They can only increase the distances. Okay. So now the nice question is, let's do a casework on the length of the path that I'm finding from S to T. Let's say that the length was some number L, in this case 4. The question is, how many times can I possibly augment with paths of length 4? Okay, or generally, for any fixed L, how many times will we augment with a path of length L? So if I'm only looking at the augmentations with paths of length L, this means that the distance from S to T was L, and I was doing these augmentations and the distance was not changing. So going back to this picture, every time I was augmenting, I was adding those magenta edges to my residual graph, but none of those edges got added into my nice graph. Okay, so does my nice graph remain the same? I mean, I'm not getting any new edges. Actually, no, because I will lose some edges, right? So when I was finding this blue path from S to T, what do I do when I augment it? I say, take the edge with the smallest residual capacity and basically send as much flow as possible through that edge, right? So that edge would be saturated. So on that edge, the capacity would become equal to the flow, which means that the residual capacity becomes zero, which means that there is at least one edge, one of these edges, I don't know which one, the one that has the minimum residual capacity, but it can be anywhere. There is at least one of them that gets removed from the residual graph. And of course, if it gets removed from this, it will also get removed from my nice graph, because I said my nice graph is just a subgraph of my residual graph. So every time that I'm finding a path like this from S to T, I'm losing one of my edges. And this continues until I can no longer find a path of the same length from S to T. Okay. So how many times can this happen? Every time I'm losing one edge. So the number of times that it can happen is E, or the number of edges. Or actually, I think we called it M, right? So the answer here is just M. So for any fixed length L, the number of times that my DFS finds a path of length L and augments my flow using a path of that length is at most the number of edges, M. Okay. Actually, it might be 2M because I'm talking about the edges in the residual graph. So let's say OM. Okay. Great. So what does this mean? How many augmentations can I have overall? So for every length, I can have M augmentations. But the length of the path from S to T can be at most N, right? Because the path can at most see all of the vertices in my graph. So I'm going to do N times M augmentations at most. But how much time does every augmentation take? Every augmentation is just a BFS. And a BFS takes OM time. So my total runtime is just ON times M squared. Because I have N times M augmentations, and every augmentation is a BFS that takes OM time. Okay. Now, this is finally polynomial time. And very importantly, it doesn't depend on the amount of the flow. And because it doesn't depend on the amount of the flow, I also don't need the assumption that I had in Ford-Fulkerson that all of my capacities are integers, right? I can have real capacities here, it works. Okay, great. So again, the observations here were very simple. The observations were that these magenta edges, they would never decrease the distance from S to T. So if you're finding your augmenting paths using a BFS, your paths either remain the same length or they become longer over time. And then for every length, we just asked how many times can I do augmentation with this particular length? And we saw that we can do M times. So the total runtime was ON squared. Okay. As you see, this was a very small change in the algorithm, but the analysis is suddenly very different. And the arguments for why we have this runtime is also very different. Okay. I want to show you one more improvement here. And actually, this is an improvement that some Russian guy found even before Edmonds-Karp. And this is called Dinitz algorithm, Dinitz's algorithm. So this is based on the same idea that we used here, the idea of this nice graph. And the observation is that I don't need to do my BFS over and over again. I can just do the Edmonds-Karp algorithm, but instead of doing a BFS for finding each path, I just do one BFS and I find this graph, right? And then I use this graph, I use this nice graph to do a ton of augmentations. Okay, let's see how this would work. So let's say this is my nice graph. I'm copying it. So remember, this is my nice graph, which is a subgraph of my residual graph. And I'm just finding a path in this nice graph. And I know that this is the path that would be found in Edmonds-Karp as well. And I do the augmentation. Now, when we were analyzing it, we said that in Edmonds-Karp, when I do the augmentation, I lose one edge. So let's say I do the augmentation and I lost, for example, this edge. This edge is no longer there. Now I want to find another path of length 4 from S to T, right? Instead of doing another BFS, I can just look at this graph and I can ask, is there a path from S to T in this graph? Because remember, this was my nice graph. All the paths that start from S and go anywhere else are the shortest path, right? So if I can find another path of length 4 from S to T in this graph, that's also an augmenting path. And this would be faster than doing another BFS because I already have my graph. Okay, so here's what I'm going to do. I just do one BFS for every length. So for length 4, for example, I do one BFS, I find this graph. And now, using this nice graph that I have found with only one BFS, I want to find as many augmenting paths as possible. So I want to basically do all the steps of Edmonds-Karp, which found paths of length 4 and did the augmentations, all at once with one BFS. Okay, how can I do this? So I've created this graph. I know that any path from S to T in this graph would be a path of length 4. So I just start from S and I try to get to T. How do I try to get to T? Actually, kind of like a DFS. So I start from S, I take any arbitrary edge out. So let's say, for example, I start from S and I take this edge. I get somewhere, I know that I've taken the shortest path to that place. Then I continue. Let's say I take this edge. I continue, I take this edge. I continue, I got to T. I'm now happy, I augment this path. Now, when I augment this path, we said that we will lose some edge of this path. So let's say this edge is gone. Okay, I've augmented and that edge is gone. Now I'm starting at S again, trying to find another path. Okay, now how do I find another path? Well, I can just do the same thing. I start from S, I go here, or actually, let me do this time. Let's say I started from S and I went here in my DFS. Now I got to a dead end. I got to a vertex that is not T, but I also cannot move anywhere from that vertex. When something like this happens, I know that T is not reachable from this vertex, right? So there's no path from here to T. And when that happens, I know that this is a useless vertex, so I can just remove this vertex from my graph. So I just remove this vertex from my graph. And I continue again. Let's say I start from S, I go here, I go to this vertex 2, I see that this is a dead end. I remove the vertex 2. And I'm continuing my DFS. I'm going from vertex 1 to vertex 5, 6, and I get to T. So I'm happy, I augment this path. Let's say that this edge is removed. So I go to the beginning of the edge that was removed and I try to find the path to T from there. I see that there is no path, so I know that 5 is a dead end. I erase 5. Now I'm trying to find the path from vertex 1 to vertex T. Again, this is a dead end, I erase it. And finally, at this point, S itself is a dead end, so I cannot find the path of length 4 from S to T, so I erase this. And when this happens, when S gets erased, I finally know that there is no longer a path of length 4 from S to T. So this means that now I can go to paths of length 5. How do I go to paths of length 5? I go back to my residual graph and again do another BFS from S to T. And this time it will give me a path of length 5 or maybe longer than 5. Okay, so basically I did one BFS to create this graph, to create the nice subgraph of my of my residual graph. And then using this nice subgraph, I could find all the augmenting paths of length 4 that go from S to T. Our total runtime in the end becomes N squared M. What was I doing before? Before I was saying that for every fixed length, I'm doing M augmentations. But for every augmentation, I had to actually do a BFS. So every augmentation took OM. That's how I got NM squared. Now, I'm doing the same thing. For every length, I'm doing M augmentations. But how much time am I spending? When I'm augmenting a path of length at most N. And of course, the augmentation itself takes ON time. We are fine with that part, right? But how much time do I spend actually finding these paths? So let me do this. Let's say that my total runtime is going to be the time spent finding the paths plus the time spent on augmenting. Now, for augmenting, I know that I can have N possible different lengths. And for every length, I'm doing M augmentations, but every augmentation is now only taking N time, because the lengths of the path can be at most N, and I'm not doing a BFS in order to do the augmentation. So my augmentation time is NM squared. How much time am I spending actually finding the paths that I want to augment? Again, I'm finding paths for N different values of lengths, right? So my length L can be anywhere between 1 to N minus 1, actually, right? But then every time, I'm just doing one BFS to create this nice graph. So one BFS is going to take M time, right? And when I make this graph, I'm going to start from the vertex S, and I'm going to do a DFS. If my DFS is successful, I reach T, and then I augment, but I have counted that in my augmentation time. So I have to just count what is the total runtime of the DFS that is unsuccessful, that doesn't get to T. But if it doesn't get to T, it's going to get to a dead end. And whenever it gets to a dead end, I'm removing that dead end, right? So I can remove at most how many dead ends? At most N dead ends, because I have N vertices here. So this is also times N. So we sum these two together, and it's ON squared N.